So hopefully you've mastered how to set up a ratio and a proportion to solve for a missing, unknown variable. And today what we're going to do is apply that to looking at similar figures. Now this is not new. You looked at this earlier in the semester when we talked about transforming figures. This would be like doing a dilation. And so your camera, every time you take a selfie, you have dilated yourself. Every time you look at MapQuest, you're looking at the world dilated down into a map. And so today we're going to talk about this and how it looks in geometry. So the first thing you have to understand is that similar figures have two things in common. One is that they have equal angles. Angles will always be congruent when you're talking about similar figures. And so since all of these have 90-degree angles in the corner, we can say for certain that these are going to be similar. Now over here we're looking at these triangles. You can just see that this is an obtuse angle right here. So, and this is an acute angle. So you can see just by looking at these triangles that these are not congruent at all. Okay? And so these are not going to be similar. And so we say that two polygons are similar if and only if the corresponding angles are congruent. I'm going to see if I can do my best to get this on the corresponding. And you remember from last unit what corresponding looks like. It's in the same position, are congruent. And we all know that congruent means the same. And the measures of the corresponding sides are proportional. And it's proportional by what we call a scale factor. And you know how to set up a proportion from last unit. So the symbol that we use to show similarity is just that squiggly line. And so we know that this means congruent, and just a squiggly line means they're similar. So that means they're not equal, but they're similar. And so here we've got this example where we're saying that ABC is congruent to DEF. So ABC is similar to DEF. So I'm going to go ahead and draw two triangles, but they're not going to be exactly the same. But what I am going to say is that they're similar. So I'm going to call this A, B, C, and this one will be D, E, F. And be careful that you put your letters corresponding to each other. So if I wrote D, E, F above A, B, C, I know that A and D correspond, B and E correspond, and C and F correspond. So I know that the corresponding angles are going to be congruent. And I know the corresponding sides have the same ratio. All right, so now I can say that I'm going to go ahead and talk about my angles. I can say that angle A, right here, is congruent to angle D. I'm trying to get it on the lines, but my thing is a little bit off today. And then I can say for certain that angle B is congruent to angle E. And lastly, I can say that angle C, 3 marks here, 1, 2, 3, 1, 2, 3, is congruent to angle F. Because in similar figures, the angles are always going to be congruent. And now what I can say is that the same ratio is going to apply for side length AB and DE. I can't say that they're congruent, but I can say they can have the same DE, and I can do the same for EF and BC. Lastly, AC and DF. Now, if the scale factor is greater than 1, this is just like when we did a dilation. When the scale factor was greater than 1, we called it an enlargement. When the scale factor is less than 1, you're going to reduce the image. Okay? So let's look at some examples here. First thing when I'm looking at a scale factor is I always think of new shoes over old shoes. And so here they're telling me my scale factor is 2. So I know that this is going to be 2 times larger than this one. So I always like to label my images. That's the old image and this is the new image. And so I want to find the dimensions of the figure. Well, first of all, I know the angles are going to be the same. And all I do is I take my scale factor of 2 and I'm just going to multiply each of the sides by 2 to get my new, so 9.5 times 2 is 19. So this side has a side length of 19. This side is 14, 14, and 4.5 times 2 is 9. And so my new image has side lengths corresponding. And over here, you'll notice that I'm taking a larger image. So this time my old image is larger than my new image. So I know that my scale factor has to be less than 1 because it's a reduction. And so I'm just going to take each of these and divide them by 2 or multiply them by 1/2. So 8 divided by 2 is 4. 10 divided by 2 is 5. Another side of 5. Another side of 4. And these 2 sides on the inside are 3 because 6 divided by 2 is 3. So again, that's how this is done. Let's look at some more examples. So please remember that similar figures are enlargements or reductions of each other. It's like a dilation, so think back to dilating. The amount of the enlargement or the reduction is called the similarity ratio. And so as you know, a ratio can be written in several different ways. And then the ratio of the scale factor lengths of the similar figures is called what we call the scale factor. And so if we are wanting to determine if the polygons are similar, we're going to show our work and justify our answers. And so the way we do this is we're going to look, we're going to label this old, and this is new. And so you always want to do new over old. And so to get my scale factor, what I would do is look at my corresponding sides, which is here, this 12, and this 16. So I'm going to do new over old, which is 12 over 16. And when I simplify it, I get 3 over 4. So my scale factor in this case is 3 over 4. Now let's look at the other side and see if I get the same scale factor, because we know that one way to test if a ratio, if 2 things are similar, you got to look at all the sides. So again, I'm going to do new over old, and I'm going to use the other side. So this time I'm looking at 9 and 12, new over old. So if I do 9 over 12, and I simplify it, 3 goes into both, I end up with 3 over 4. And since my scale factors are the same, I can say for certain that these 2 images are in fact similar. All right, let's look at number 2. What I'm looking at is, again, this is going to be my new, and this is my old. Excuse me, I'm going to do that over again, because that is not true. The one you start with is your old. So this is my old. This is my new. So I'm going to do 24 over 8. It's 24 over 8 equal to 14 over 7. And is that equal to 12 over 6? Well, the answer is no. These are not equal. These are, those 2 are, but since that one's not equal, no, this is not similar. And number 3, you can just check the angle measures. I don't even have to worry about the side lengths because it pops out at me right here that these angles are not the same. And because we do not have the same angle measures, no, they're not going to be similar. So those are ways to test whether you have similar figures or not. Now what we can do is we can set up proportions to find the values of missing lengths. So I know in this figure that these 2 triangles are in fact similar. And now what I want to do is I want to figure out what x and y are. So first we have to write proportions for the corresponding sides. And again, I'm going to call this my old, and I'm going to call this one my new. So if I'm setting up proportions, I know that I can put y over 45. And I know that I can put 15 over 2x minus 3. And lastly, I know that I can put 30 over 50, because those are my corresponding sides. And so these should all equal up to each other. And so if I wanted to write the proportion to solve for x, well, here I would use these two. I would use 15 over 2x minus 3 and equal that out to 30 over 50. And last class you learned how to solve a proportion. So you would just simply cross multiply, find your cross products. So this would be 50 or 15 times 50, and set that equal to 30 times 2x minus 3. And so what do I have here? I have 750 equals 60 x minus 90. I'm going to add 90 to the other side, and that gives me 840 equal to 60x. Divided by 60, and I get x equal to 14. Now I know what this side length is. I just simply do 2 times 14 minus 3. And I know that that side length is 28 minus 3, which is 25. All right. Now we're going to solve a proportion, write a proportion to solve for y. There's a couple ways I could do it. I could put my new value in here, and I could use this equation, or I could go back and I'm going to use what I know. So I know this, and I have numbers here. Remember, when you're solving for a variable, you can only have one of them. And so I'm going to do y divided by 45 equals 30 over 50. Cross products, and I end up with 1350 equals 50y. Divide by 50, and I end up with y equals 27. So now I can say that this side over here is 27. So just remember, when you're trying to set up your scale factor, I always think of the fact that I prefer new shoes to old shoes. And so you're always going to put your new shape on top and your old old shape on the bottom. So what do I mean by this? So if I wanted to find the similarity between AD, BC, and WZYX, I know that this is going to be my old, and this is my new. So when I'm trying to set up my similarity ratio, what I'm going to do is I'm going to put old on top and new on the bottom. So this side is my new side, this side is my old side, so it would be 4 over 12, which is equivalent to 1 over 3. And so my scale factor is 1 over 3. So if I want to find my missing side lengths, I just simply take the old shape, times it by 1/3. So 9 times 1/3 is 3. 12 times 1/3 is 4. And over here I know that 9 times 1/3 is also 3. So that's how I can find my missing side lengths. All right, let's try that again. This time, my old shape is small, and my new shape is larger. So I can say that I predict my scale factor to be a whole number. So I want to know the similarity ratio. So again, it's new over old. So I'm going to choose this side right here since it's the only side I know. So it's going to be 15 over 3. And then my scale factor is just simplifying that. So 15 divided by 3 is 5. So my scale factor in this case is 5. So if I wanted to find the missing length of each side, if you want to test it out, go ahead and pause the video and work it out and see if you can figure out the missing side lengths. What's cool about this scale factor is not only does it work for side lengths, it also works for the perimeter. So if you find the perimeter of the old shape by adding up all the sides, you get 14. And the perimeter of the new shape, when you add up all the sides, you end up with 70. And what you'll notice is also 14 times 5 is 70. So scale factor works for side lengths as well as the perimeter.